In this lesson, we're going to look at trigonometric integration, or integration involving trigonometric functions. Okay, in order to be able to integrate a trigonometric function, you first need to know what the derivatives of the 6 trigonometric functions are. So let's quickly review that before we dive into these problems. Okay, I have them listed here. So we have the derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of tangent is secant squared. The derivative of secant x is secant x tangent x. The derivative of cosecant x is negative cosecant x cotangent x. And the derivative of cotangent x is negative cosecant squared x. So just a couple of things you can make note of. All of the co-functions, cosine, cosecant, cotangent, their derivatives are negative. Another thing that helps me remember some of the derivatives are just patterns. Secant and cosecant have a similarly formatted derivative, right? Secant, tangent, cosecant, cotangent. Cotangent and tangent also have sort of similarly formatted derivatives. So if you don't have them memorized yet, you should have your list of derivatives sitting next to you so you can use those to work on the integration. Excuse me. But hopefully you will have them memorized in no time at all. Alrighty. So let's get started on the integration. Okay, as I've said before, I love integration. I love trigonometry, so this is a very joyous unit for me. Okay, so these first 4 problems are going to be review, just sort of baby integration problems. So, number 1, let's zoom in a little there. Okay. The integral of sine. Well, first of all, we've got a sum. You don't have to rewrite this at all, but just a reminder that the integral of a sum is the sum of the integrals. So this is the same thing as sine x, the integral of sine x dx, plus the integral of cosine x dx. So we just need to integrate each piece individually and add them together. Well, what is sine the derivative of? Well, the derivative of cosine is negative sine. So this must be the derivative of negative cosine. And then the derivative of cosine is the derivative of sine. You know, it's nice when you integrate, it's very easy to check your answer. Just take the derivative of your answer. So if I look at my answer and I take the derivative of this, well, the derivative of negative cosine, it's negative sine. The derivative of sine is cosine, and the derivative of a constant is 0. And that's what I have in my original equation, sine x plus cosine x. So I know that my integration was done correctly. All right. Number 2, negative 5 secant squared x. So just another reminder, no need to rewrite this, but you can pull any scalar or a constant multiplier out of an integral. So that's just going to be negative 5 times the integral of secant squared x dx. Certainly no need to rewrite it like that, but whatever my integral answer is for secant squared x dx, I'm just going to multiply it by negative 5. So this is going to be negative 5, and secant squared is the derivative of tangent x. So this is my answer. This is my final answer. And again, people always ask me, well, why isn't it negative 5 times c? Why isn't it negative 5 times tangent x plus c? But when you distribute the negative 5, you get negative 5 tangent x minus 5c. Well, negative 5 times a constant is just a constant. So I can write that as some constant plus c. Okay, number 3. So I have 6 times cosine, and cosine is the derivative of sine, minus 3 secant x tangent x, and secant tangent is the derivative of secant x. Oops, I missed a 3. Let's throw a 3 in there. All right, there we go. Okay, number 4, we have a combination of integral of a trigonometric function with a polynomial here. Okay, so 8 cosine, we already integrated sine. We know that sine is the integral of sine is negative cosine. And then let's remember how we do this. So the exponent I'm going to wind up with, if I integrate x squared, is x cubed. And then the coefficient is my old coefficient divided by my new exponent. Okay, so plus 1/2 plus 1, well, that's going to be 3/2. And then I have my old coefficient divided by my new coefficient. Okay, well, let's figure out what that's going to be. So here I have 3 divided by 3/2 is 3 times 2/3, which is just going to be 2. So, oh, turn off the phone. No time for phone calls when we're doing trigonometric integration. Okay, so I have negative 8 cosine x minus 2/3 x cubed, and then this is going to be equals 2, oh no, sorry, plus 2 x to the 3/2 plus c. Okay, so those are all review problems from last Thursday and last Thursday. I think that pretty much covers it. Okay, now 5 and 6 are also going to be review problems, but we're going to combine 2 ideas, the idea of trigonometric integration and the idea of U-substitution. Okay, so we have integrated the cosine of x, the sine of x, all of the trig functions of x. But what we haven't integrated is a trig function with an argument that's not x. So here we have an argument that's 6x. Now, eventually you're going to be able to do this without doing a U-substitution, but that's how we're going to start today. So I'm going to say, let's let u equal 6x, okay? And I'm going to rewrite this equation using that U-substitution. So oops, that's not very dark. Okay, here we go. So let u equal 6x. Okay, now, when you make a U-substitution, you're going to change everything that is u into, everything that is x into something that is u. So that means I'm also going to change the dx into something involving u. If I take the derivative of this equation, the derivative of u is du. The derivative of 6x is 6 dx. Okay, now, I don't have 6 dx, I just have dx. So I'm going to divide both sides by 6, or think of it as multiplying by 1/6. And I get that dx is 1/6 du. Okay, now I'm going to rewrite my integral now. So this is going to be the integral of the cosine of u, and then times I have 1/6 du. Now remember what I said, when you have a scalar in your integral, you can pull it out. So I'm going to take that 1/6 and pull it out. So this is 1/6 times the integral of cosine u du. Well, we already know how to integrate cosine u du. Cosine is the derivative of sine. So cosine u du integrates to sine u. So I have 1/6 sine u plus c. But I always have to go back to the original variable from the problem. So now I'm going to get rid of the u and put the x back in, and I get 1/6 sine 6x plus c. Okay. All right, let's try another one just like that. So we're looking at number 6, and I'm going to follow the exact same steps I did for number 5. So I'm going to let the argument be u. So let u equal 10x. I'm going to take the derivative of both sides of that because I need to know what dx is going to equal. So the derivative of u equals 10 times the derivative of x. Du equals 10 dx. And I need to get the dx by itself, so I'm going to multiply both sides by 1/10. So this is 1/10 du equals dx. Okay, we've set up the U-substitution, so now I'm going to go back here, and I'm going to say, this is the same thing as the integral of sine u, and then dx is 1/10 du. And remember, I can pull the 1/10 out. So that's 1/10 sine u du. Well, we already know how to integrate sine u du. The integral of sine u is negative cosine u. So this is negative 1/10 cosine u plus c. And that's because the derivative of cosine is negative sine. My last step when I'm doing a U-substitution is to go back to the original variable of integration. So go back to x's. So I'm going to replace the u with what I assigned it to, which is 10x. So there's my final answer. The integral of sine 10x dx is negative 1/10 cosine 10x plus c. Okay. Okay, so we've done a little bit of review. We have practiced some sort of baby U-substitution. And now we're going to take this one step further. Okay, before I get into the next type of U-substitution, I want you to look at some patterns in derivatives. Okay, so we're going to take the derivative of these functions. So first I have y equals the sine x to the fifth. Now remember, this is the same thing as sine x quantity to the fifth. So first I'm going to do the exponent rule. So this would be 5 and then sine x to the 4th. And then the chain rule tells me I need the derivative of what's inside. The derivative of sine is cosine x. So again, what would this be? It's the same sort of expression, but to the 10th. So the derivative of sine x to the 10th is 10 sine x to the 9th cosine x. Well, what if I have the derivative of a power of cosine? So again, we're looking at a function that is a power of something, cosine x, quantity to the 20th. So I need to use the exponent rule first, and then use the chain rule and take the derivative of what's inside. So this is 20 cosine x to the 19th times negative sine x. Or I'll rewrite that as negative 20 cosine x to the 19th sine x. And then following the same pattern for this last one, I'm going to have 8 cosine x to the 7th times negative sine x. And I'll just clean that up to negative 8 cosine x to the 7th sine x. Now, I want you to look at these patterns and think about going backwards. So remember that another word for integration is anti-differentiation. So, for instance, let's go back to our basic derivatives. If the derivative of sine is cosine, then if I integrate sine, or cosine, I'm going to get sine. So let me write the parallel here. The integral of cosine is sine. Plus c, of course. But the integral of negative sine is cosine. Plus c. And so on. So if you can take the derivative of a function and get some other function, then you can integrate that other function and get your original function back. Okay, so I just used the first three, but integration and differentiation are inverse operations. You do one, you do the other, you should get back what you started out with. Okay, so let's go back over here. If I took the derivative of sine to the 5th x and I got this, if I integrate this, I should be able to get sine to the 5th x. So that's the idea behind the next couple of problems, okay? Okay, so what you want to see in the integral is a function and its derivative. So I see that my function is going to be sine x, and its derivative is going to be cosine x. Now, you can have your function to any power you want, but you can only have the derivative to the first power. Okay, so I'm going to do a U-substitution again here. What do I want to make u? I want to make u equal the function. So u is going to be sine x. And then I'm going to take the derivative, du, and I should get the other term. So this is cosine x dx. The U substitution is just going to make it a little more familiar for you to integrate. So when I rewrite this, this is the integral of, well, this is u to the 6th And the cosine is part of the du. This whole part is du. And this whole part is u to the 6th. Well, that's an easy thing to integrate, right? That's just an exponential integration, or sorry, a polynomial integration. So that integrates to 1/7 u to the 7th plus c. Well, what's my last step when I do a u-substitution? I have to get rid of the u and go back to the original variable. So this is 1/7 sine to the 7th, sine x to the 7th plus c. People always ask me, where did the cosine x go? The cosine x was part of the derivative, and that disappears when you integrate. If you look back up here at the pattern we had in number 7, if I integrate the right, I should get what I started out with. So look at, if I integrate 5 sine x to the 4th cosine x, I should wind up with sine x to the 5th. All right, let's do another one. So here I have cosine x to the 12th and sine x. So now I'm going to say, let's let u be cosine x. Then du is, well, the derivative of cosine is negative sine x dx. Well, that means, since I only have sine x dx, I'm going to move the negative sign over to the other side of the equation. It's like a -1 scalar. And I get that negative du is sine x dx. All right, so let me rewrite this. So using my u-substitution, this is the integral of u to the 12th. And then sine x dx is negative du. So remember, this negative sign is like a -1. And you can just put that outside of your integral. So I'm just integrating u to the 12th du. And that integrates to negative 1/13 u to the 13th plus c. And then, of course, my last step is put your original variable of integration back into the problem. So negative 1/13, u is cosine x. Cosine x to the 13th plus c. There we go. Okay, now we're getting into a couple of doozies at the bottom. Throw a little fun in there. Okay, so let me explain to you the two possible things you're looking for. You are either looking at that integral and saying, I look at that integral and that is the derivative of something. So let's go back over to the first couple of problems. For instance, if I look at number 3, I know cosine is the derivative of sine. I know secant tangent is the derivative of secant. That's my thought process when I integrate those. But over here, the second thing you could be looking for is you could be looking for a function and its derivative, both in the integral. A function and its derivative. Okay. So you're either looking for everything you see to be the derivative, or you're looking for a function and its derivative. All right. 10 is a little bit tricky. You know what? Let's do 11 first. 11 is sort of more in the pattern that we were just talking about. And in 11, there's actually several ways you could approach 11, but the first thing that pops into my mind is that I see a function and its derivative. Okay? So, what do I mean? The function is sine. The derivative is cosine. Remember that I said the derivative should never be to anything but the first power. So this is cosine to the first. So how does that work? Well, remember, I could rewrite this equation as sine x to the negative third cosine x dx. And then this is a problem very similar to problems 8 and 9. What would I make u? If I were doing a U-substitution, what would I want u to be? Look back at 8 or 9. U should be the function raised to some power. Du can only be raised to the first power, which means I want u to be sine x, which means du is cosine x dx. So I have a u to the negative 3, and I have a du. All right, so my integral is, oops, let me move this up a little. My integral is u to the negative 3 du. Well, that's a simple polynomial integration. U to the negative 3 integrates to, my exponent should become negative 2. I'm going up 1, and so this needs to be 1 over negative 2, or negative 1/2. Lastly, I'm going to put my original variable back in the problem, and I get negative 1/2 sine x to the negative 2 plus c. And I could write this two ways. So I could write my answer as, I'm going to get rid of my negative exponent. Sine x to the negative 2 goes into the bottom, 2 sine squared x plus c. Or you also could have written this as negative 1/2 cosecant squared x plus c. So either of those would be acceptable. Okay. All right, let's see. I'm just going to show you one more way you could have done this problem. Now, this is probably not a way that is intuitive to most people, probably not the first thing that pops into your mind, but I just want to show you because the trigonometric integrals can be done many different ways, and the confusing part is they can result in many different answers. So, for 11, cosine x over sine cubed x. Oops, what's going on there? Okay. So, there are many trig properties you could use to rewrite this. But the things that pop into my head are, I can write this like this, separate it, okay, so that's sine cubed. Why would that be useful? Well, this is cotangent, cosecant, and cosecant. Okay. I'm just going to rewrite these in a slightly different order. So I'm going to write cosecant first. I'm going to completely flip the order. Cosecant x, then cosecant x, cotangent x, dx. Well, why is that useful? Again, you would really need to know your trig properties for this to pop into your head. But if I wrote it this way, I could say, well, let's let u equal cosecant x, and I'll use this cosecant x to be u. And then du, what's the derivative of this? The derivative of cosecant is negative cosecant x cotangent x dx. Okay, so this is like a negative du. So now if I go back and rewrite this, I have the integral of u negative du, which is just negative the integral of u du. U to the first integrates to 1/2 u squared plus c. Last step, put your original variable of integration back in, put the u back in, negative 1/2 cosecant x squared plus c. We got the same answer we got before. But if you did your problem using sines and cosines and you got this answer, you might think your answer is wrong if you look in the back of the book. So just be aware, with trigonometric integration, there can be often many ways to approach a problem that result in different answers, all of which are correct. So this is another case where if you get an answer that doesn't match the back of the book, don't freak out. Just think, are there any trig properties that you could use to turn one answer into the other? All right, 2 more problems. Okay, all right, back to number 10. So number 10, if you think about the 2 things I told you, either you're looking to see a function and its derivative, like we have in number 11 and like we have in numbers 8 and 9, or you're looking to see that what you have is the derivative of something. So hopefully you recognize that secant squared of something is the derivative of tangent. But then there's other stuff going on there. So this is a U-substitution of the argument. So we're going to say, let's let u equal 4x cubed. Then du would equal 12x squared dx. Well, it's not written this way, but if I regroup things here, just do sort of a reorganization, I can put the x squared over by the dx. So I have secant squared 4x cubed, and then I have x squared dx. We'll just group those together. Well, that is useful because I can get rid of the x squared dx. If I multiply both sides by 1/12, move the 12 over to the other side, I get 1/12 du is x squared dx. So, back to my substitution. This is going to be secant squared u, secant squared u, and then this is 1/12 du. So remember I said I could take the 1/12 out, and I'm just integrating secant squared u du. And secant squared u is the derivative of tangent u. Last step, put the original variable of integration back into the problem. So I get 1/12 tangent u is 4x cubed plus c. Whew. Okay, last problem, number 12. All right. Number 12 is for somebody who really loves their trig identities. It is tricky, tricky. Okay, so sine cubed is not the derivative of anything. But we also don't have sine and its derivative. We would need a cosine. So here's the trick. We are going to use a Pythagorean identity here to create an expression that has a function and its derivative. Now, the Pythagorean property is used with squared trig functions. So what I'm going to do is I'm going to split this up. I'm going to split it into a sine squared x and a sine x, because that makes sine cubed. And then I'm going to use the Pythagorean on just the sine squared. Who thought of that? Super creative, right? 1 minus cosine squared x. So this looks complicated, but it actually turns into a very simple integral, or I should actually say two very simple integrals, if I multiply it out. So when I multiply it out, I'm going to get 1 times sine x dx, and I'm going to actually write this as two separate integrals. And then I'm going to get minus cosine squared x times sine x dx. Well, this is very nice, because this integral is very easy. The integral of sine is negative cosine x. And then we need to figure out what's going on here. Well, this is an integral very similar to number 9. If you look back to number 9, I would make u cosine x here, and I would make du, well, du is negative sine x dx. Okay, which means since I only have sine x dx, I would, what do I want to do here? I want to multiply the negative 1 over to the other side. So negative du is sine x dx. All right, so let's rewrite the integral. It's u squared negative du. But that can just come out as a plus, right? So I have negative cosine x. The negative comes out, makes this a plus, the integral of u squared du. Now this is a nice simple polynomial integral. Negative cosine x plus the integral of u squared is 1/3 u cubed plus c. And finally, my last step, get rid of the u, put my original function back in, and I get negative cosine x plus 1/3 cosine cubed x plus c. Oh, that's a good one. Okay. It's nice to end on a nice, satisfying, challenging one. All right, so that is trigonometric integration in a nutshell. And now you have the rest of the period, the last 10 minutes, to work on the homework, which is on the back of this handout. And you should also have received an answer sheet for that. Please do the homework on a separate piece of paper showing all work for the integration. All right, happy Thanksgiving.